Okay. Well, thanks for coming and listening. I'm going to be talking about pipeline proving and a bunch of other stuff aside from that, which is, I'm going to call it a trick that we do at Hylé to enable practical ZK proofs for smart contracts and applications. So I'm Lancelot. I'm the co-founder and CTO of Hylé. Very high-level explanation of Hylé is that we're an L1 blockchain targeting specifically ZK applications of any kind. And we're not yet released. We're expecting our testnet to be coming in a few months. So what I'm going to be talking about is how dApps will be written in the future, thanks to zero-knowledge proofs. And this will happen whether or not it happens on Hylé, because zero-knowledge proofs is going to take over, I think, for smart contract development, just because of the scale benefits and the cost benefit it offers, and also the flexibility, because you can write in Rust with the ZK VMs, you can write in kind of anything you want, and it's much more similar to writing a real application than something else. So rollups are good. People like rollups. People have been doing so many rollups that you can no longer count them, even if you go on L2 beat. But they could be better, and this is what I'm going to be talking about. The main advantages of rollups is that state commitment is maintained on the L1, so you got the security of the L1 for settlement. State transitions are validated by ZK proofs for ZK rollups. I'm not going to get into optimistic proofs, but at the end of the day, it's kind of a similar idea. But they're usually permissioned. When you're operating your L2, only the L2 sequencer can usually send state transitions. There's an exception to this whole question of escape hatches, which is very interesting, but nobody's really implemented them in practice well. And obviously, indexation of the data is trustless. If the rollup is posting their state diffs to the L1 for data availability, but you have to rely on other actors for that. The way it works, state commitments, you basically Merkleize your state typically, and then all you store on the layer 1 blockchain is the state commitment, which is just a hash. And 99.99% of the data remains on the L2. So all you have to do on the L1 is the state commitment, which is very cheap because it's not that much information. And on the L2, you have the actual state of whatever application you build. This enables you to make stuff that's much, much bigger in the size of the state you have than what you could do on Ethereum L1, whilst not compromising on the security of the settlement. How do you then change the state is the question. And the basic idea is that each transaction, because blockchains are state machines, each transaction is just a proof of a state transition. So you go from an initial state, which I've represented here with the green dot, to a new state with each transaction. And so by sending ZK proofs, you can prove the state transition from the green state to the blue state, and then from the blue state to the red state, and the L1 blockchain verifies the ZK proof, updates the state commitment trustlessly, and everybody's happy because then it reflects the actual L2 state. Of course, if you're looking only at the layer 1 blockchain, you won't be able to reconstruct the full iceberg. So what you need to do is be able to have indexers or DA. That's the whole problem of data availability that people talk about. And so on Ethereum nowadays, if you'd be doing that, you'd be doing it with blobs. You pass blobs, and then people can read the blobs. They're available, guaranteed for 30 days. And so either the user can read the blobs and re-verify the proofs themselves and reconstruct the state locally for some applications, or you use an indexer which can do that for you, and potentially the indexer will be itself will prove via recursion that its state is correct based on the state of the L1. And then the rollup infrastructure usually provides that as a service when you use if you use Starknet, or if you use any other, or zkSync or any other ZK rollup, you'll just interact with Alchemy or Infura like you would on Ethereum L1. You get access to the state of the chain. You don't really know that you're actually interacting with the L2, and you don't actually care, because if you have a question of trust, you could check with proofs of inclusion from the Merkle tree that your stuff is indeed what's being secured by the L1. An interesting development in that area is actually base rollups. And so what people have realized is that you can do something kind of similar to what rollups have been doing on Ethereum, but more on the L1. So the basic idea is that this is the same slide as earlier for a reason. Basically, instead of sending your transactions to the L2 sequencer and having the L2 do whatever it wants and occasionally send blocks to the L1 that act as like state commitments, you send your transactions to the L1 directly. You send your transactions to Ethereum. Ethereum then sequences them, and then you read the order in which transactions were sent. You basically re-execute that in your server. You generate a fraud proof or a ZK proof, and then you go back and you send the transaction that's the settlement transaction on Ethereum. So we kind of go from a system where you send the transaction to the L2, and the L2 is kind of a trusted intermediary to send it to the L1, to a system in which you send the transaction to the L1, and then anybody can kind of come in, see what's committed on the L1, and actually settle the state transitions on the L1. It's much more trustless potentially because you don't have this need for like an L2 intermediary. And so this enables you to do like, well, this is what we've been doing on Ethereum right now. On Ethereum, you got the L1 and you got bridges to various L2s, because if you have rollups that are not based, you need to bridge because you need someone to do message passing between the states because the sequencing is not happening on the same chain. The problem here is that if you're trying to do based ZK rollups and you're trying to do your state transitions with zero knowledge proofs, well, you run into a few issues in practice. And if you look at some of the blockchains that have been doing this, for example, Mina, the Mina blockchain has been running with ZK proofs since 2017 or something like that, which is crazy to think about. But their performance is not great. Their throughput is pretty bad because they have these issues. You got three problems. The first problem is a composition problem. It's basically hard to call other contracts using ZK. If you're on Ethereum, you just call something else with ZK. That's kind of difficult by default. You got the proving problem, because obviously if you're trying to generate ZK proofs, it takes time. You're going to add latency, and you're going to add costs a bit of cost as well. And the biggest problem is actually the parallelization issue, because ZK in some sense isn't commutative. So let me get a little more in depth into each of those and how we can improve rollups. So the first thing is that what you'd like to do is to do composition. So to give like a random example, let's pretend NFTs are back in fashion. You want to prove that you own CryptoPunk to be able to play on-chain Tetris or something. What you would have to do typically is do recursion. So you prove that you own a CryptoPunk, and you verify that proof within your ZK Tetris program. So you have to write the verifier for your proof system in a provable language and then prove that. This can work, especially if you're using the same proof system for both, but if you're using different proof systems, it's difficult. And there's also another issue, which is that if you want to change, for example, from a CryptoPunk to a Bored Ape or whatever, or if you want to change the game, you have to like redo the whole thing. You have to change the state of both. Like they're really tied together. Composability, on the other hand, enables you to kind of refer to one or the other like you would on Ethereum, as if they were just different contracts. So you could say, well, you have the CryptoPunk ownership NFT contract, and then you make a game, and you in that game you can handle very easily different type of like identity NFT ownership. And if somebody changes the CryptoPunk contract, you would not have to change the Tetris contract, because they no longer are so tied together. So this is like one of the big advantages. And the way you can get that, and the way we give that on Hylé, is that you have to do shared sequencing, essentially, on the L1 layer, so that you can have atomic composability. This is one of the things that are essentially impossible right now on kind of any of the existing blockchains, because none of them have native support for that. But we have it at Hylé. Second problem, pretty straightforward. Proving time. Let's say you have an auction. You want to send a bid on an auction, but it ends in 10 seconds. You'd have time to send your transaction, but you won't have time to prove it. because proving is usually kind of slow. And so if you have to wait for your proof to send a transaction on chain, well, you're going to be unhappy because you're going to miss the deadline. So that's kind of annoying. The second problem with proofs is that what happens if you have two people that are seeing the same on-chain state for the auction and want to make a bid, but let's say that the blue guy sends his transaction faster than you because he's generated the proof faster than you. When your transaction arrives, because both of them are like atomic state transitions starting from the green state, well, the first one's already switched to the blue state on chain, so yours can't be settled because, you know, it's no longer the green state that's on chain. So that won't work, and we literally cannot settle the second transactions. And this was one of the big problems, for example, at Mina. This is also one of the reasons why ZK rollups are permissioned, because it doesn't actually work all that well otherwise. The solution to both of these issues is the title of the talk, pipeline proving. Basically, it's kind of similar, if you know what those guys have been doing, to what Monad has been doing with deferred execution. It's kind of a similar idea. You first sequence the transactions. So you do the same thing that you send blobs, basically. People say, I want to make a bid on this thing. I want to commit however much, like, I don't know, 100 USDC. And you can sequence both transactions independently because they're not actually doing anything on the chain. You're just settling, you're just sequencing that some stuff is going to happen. Once the transactions have been sequenced, included in a block, voted over by consensus, it's basically set in stone. And so at this point, you open up a window for people to prove that the transaction they committed to is indeed correct. So basically, if you were sending a blob that you want to auction on something with 100 USDC, you would then have to prove that you indeed have a balance of 100 USDC. And what happens, for example, when you're moving them, staking them, what the state transitions in the various contracts that are involved are. And then you'd send the proof, and once the proof is arrived, the chain can settle the state changes because it knows where we're at. And one of the interesting things here to note is that it doesn't just solve the latency issue. So it moves like the proof generation latency is moved out of the critical path for transaction inclusion. So you can take more time, which means you can use slower computers, which is cheaper for generating the proofs. And you don't have so much pressure. You don't have to do it client-side. The second thing is that it solves the parallelization issue because you know what the state transitions are going to be. You know that it's going to be from green to blue to red, and you can generate the proofs accordingly. You don't have to start from the initial state that you saw when you launched the initial transaction. This kind of like setup, which is kind of an evolution of what base rollups are, in a way, is what we're calling unchained applications, because their applications are no longer limited by the chain, restricted by the chain. And like basic idea is that you have blockchains that will act as custodians of data integrity. They're like truth machines, blockchains, thanks to zero knowledge proofs, but they won't actually give you the full state because you don't actually care about that. And blockchains are like terrible at storing data because they're replicated so much, which is very, very inefficient. You know, if you store your stuff on S3, you're not gonna see it disappear because we know how to do data resiliency. They do sequencing, which allows you to have like this atomic composability property, which is really important for composition. They do data availability so that it's actually trustless and everybody can come in and index stuff. And then you want to have native verification for settlement because it's faster, it's more efficient, you don't have to re-execute anything. You get the scalability from ZK, you get the efficiency, and you also get the opportunity to integrate many different kinds of like proof systems and developer ecosystems and language types because the ZK VMs have different trade-offs. And if you have pipeline proving and native proof composability, you can actually use the chain kind of with the same developer experience as if you were doing Ethereum L1 stuff. But you know, you're not writing Solidity, you're not limited by the state size, and you don't have $20 for an ERC20 transfer. And you can build like a bunch of new kind of applications that you wouldn't be thinking of before with this technology. You could do permissionless peer-to-peer on-ramp with ZK email, people just sending money and proving that they do. You could have fully on-chain games that are decentralized by the players, so the players maintain the state, and you do just the state transition on-chain. You could do privacy things. I haven't really mentioned that because it wasn't key to what I'm saying here, but like you could have private strategies and then still commit on-chain to what you've been doing, so it remains trustless and you remain like interoperable. That's it for this presentation. So I'm Lancelot from Hylé. We got Twitter, Telegram, our website, everything. If you're interested in doing stuff with ZK, we're going to be releasing our testnet soon that you can come in and see, start playing around with those stuff. I think we're going to be the best environment for like quickly testing ZK applications, because it's actually kind of annoying if you have to deploy your own verifier and kind of know how these things work. And otherwise, we're also happy to we've got some knowledge. We're building applications ourselves, so if you want to know what kind of proof system you should use for something, you can ask us as well. I don't know if I have time for questions or, well, then if you have questions.
So say we were to make a game.
Yeah.
How would you recommend organizing that game in terms of what do we prove, what not?
Yeah, that's still kind of a, I don't think anybody's got the perfect answer to that question yet, because no one's really tried to do that in practice. But the basic idea at the moment is that you want only the game logic to be provable, because you don't really need to prove the graphics or anything like that. That kind of split architecture is still a little awkward to write, because nobody's really been focusing on actually trying to do that. And if you look at the risk, so one of the good things about the RISC-V ZK VMs, or like the ZK VMs that you can actually compile Rust to, is that, for example, if your application, if your game server logic is written in Rust, you can reuse the same code for the provable part, and for you can interop with the provable part in a non-provable context, and then use the same code to actually prove it and set it on chain. That's what we've been doing for some of our internal ERC20 logic for Hylé, but it's still pretty experimental, and I don't think there's a really good framework for that yet.
And say I have I run servers for competitive gaming. How can I make sure, or be able to prove to the world that that the players in these games I host, none of them are cheating, and that the rules are always consistent?
Yeah, so ZK doesn't fix the cheating problem entirely, because if you look at video game cheating, the big issue you have is that you don't know who's operating the game, and you literally still cannot know that. For all you know, it's a robot that's typing on a keyboard, and so you're cheating with that. What you can prove is that everybody's been playing by the same rules. So if you're doing a full information game like chess, you're fine, there's no issue. If you're doing a limited information game, you have to either have a server somewhere that's acting as an escrow for private data, or you can try doing NPC stuff. That's not a topic I'm super knowledgeable about though, so I honestly cannot get into it. But there's direct player-to-player information transfer that can happen. Then you can prove that. But you need to set up your game in such a way that people being, if someone writes a super fast AI that plays your game, you might not be able to differentiate that from a human player in any meaningful way.
Thank you.
About parallelization, you mentioned that when the example is for a bit, right? Because they try to make the kind of the same change in the state of the blockchain, try to send at the same time. For this part, when you, I mean, I try to make something with financial reports, but I don't think that, I think I need parallelization, because this is for financial institutions, so they try to up a lot of information, but they don't try to make the same proof, for example, for a bit. But I can make this, I can use parallelization for make this fast or efficient? And how can I apply the parallelization for?
Yeah, let me get back to that slide. The key idea is that what you have to do is split the sequencing from the settlement. That's like both all you have to do, and it's kind of annoying to do on existing blockchains. The sequencing gives you the deterministic, like if you start from a certain point and you apply transactions in a known order, you're always going to arrive at the same end state. So that's like sequencing is all you need for deterministic, I mean, except if you're using intent, but that's like a whole can of worms. But then you want to settle that state. So what you have to do is once it's sequenced, you can prove each individual transactions. The problem you have is if you try to do sequencing and settlement at the same time, you're going to run into order issues because you're going to start generating your proofs based on the same state, and things are going to end up looking like that, and you're going to have some stuff that you can't prove, and you're going to have to regenerate proofs, which is going to be painful because that's going to cost you more money and things like that. I didn't include this slide on this, but if you look at what base rollups have been doing, they're kind of an evolution of what Celestia was doing with sovereign rollups. It's a little more secure than that. But one of the key things of Celestia was that they're only doing sequencing, and then if you wanted to do settlement elsewhere, you would take the order of transactions that Celestia gave you, and then use that for settlement on Ethereum or an L2 or something like that.
I'm not sure about this, but I see there are some recursion proofs.
Mm-hmm.
You have your proof and you make a proof of this all proof
Yep.
in the sequencer. Hylé has something.
Yeah, actually, so one of the things we're implementing, the way we're implementing it at Hylé is that all we do is native verification of proof, so we just run the verifiers as they come. But we do support explicitly that you could have recursion where one proof stands for the verification of many transactions. So in this case, in my example here, I was going from green to blue to red, but you could send one proof that goes from green to red from the get-go. And the interesting thing about the problem with recursion usually is that, yeah, if you're trying to do different proving systems, it's kind of annoying because I don't believe that there's a noir verifier that's written for a ZK VM in Rust. So you could kind of have to do it yourself or something like that. With what we're doing, you could do recursion on the noir part and recursion of the ReZero part separately, and combine that still because the settlement logic is handled by like the node protocol. Cool. Well, thanks for listening. And if you have any other question, we're on all of the socials and we're at all of the events this week. So